there. So to answer the question about the amount of content we have left, this is where we are. Objects, but now we're talking about data structures. And I don't know if we'll finish this today, but we'll probably get pretty close to finishing it. Then we have searching and complexity and sorting algorithms. To be clear, these two topics, I'm not saying they're not important. I'm not saying they're not going to be on the exam. What I'm about to say is not that. What I'm saying though, when it comes to like the big content, this topic that we're starting today is like the last big one. The other two are more high-level understanding topics that get revisited again like in subsequent courses. And they're very important, don't get me wrong, they're very important. But this is the last big one, I'll say. Is that a good answer? Yeah? Cool. All right. All right, data structures. You know, most of the time in the course we've been talking about algorithms. Every line of code we write is part of an algorithm. It is. And a lot of times though, especially if our algorithms are working with data, we have some data structure that goes with it. For example, a list is a very general purpose data structure. We also saw other ones though too, like tuples, sets, dictionaries. But they're more specialized. You know, you don't use a set very often, but when you do, it does what it does, right? You use a set when you need to use a set, but you're probably not using it very often. A list, on the other hand, very common, right? You use a list in a lot of cases. It's a very general data structure. Dictionaries, a little more specialized, they're awesome. But again, not quite as general as a list, I'd say. Although well, really a dictionary is kind of like a generalization of a list, but that's not important right now. The data structures that we're working with and the algorithms go together, right? Like if I'm doing a linear search, I'm doing the linear search on some like data structure, right? Like a linear collection, like a list. So the algorithm and the data structures go together. Now, at the end of the day, if you were to go take the list class and open up the hood and look under it, you're going to see a bunch of algorithms. The algorithms inside there are what make up the data structure, but we're interacting with those algorithms at a higher level of abstraction. We are interacting with a list. How many of you have looked at the code that's inside the list class? Right? Exactly, you haven't. And that's the point. Because you don't interact with those algorithms that way. Effectively, you are every time you interact with a list. Obviously, the underlying mechanics is working. But you don't think about it at that level. You're thinking about the list. And you're interacting with that data structure. So even though the data structure is just a collection of algorithms under the hood, we're thinking of it as this different thing because of its level of abstraction we're reasoning about this thing. So data structures, algorithms. So the data structures are great, you know, they store data. And a lot of times these data structures also come with some handy functionality, things like the ability to index them, like a list. You can index the list to get specific information. You can do like efficient lookups, like if you've got like a dictionary, for example. They're easy to search, linear data structures, ordering in the data like a list. And I keep saying this, but I'm going to keep saying it. There's a difference between ordering and sorted. Ordering just means that the order that things exist matter. Sorted is a little bit more specialized in that they are sorted based on the order that they are in is based on some important property. So when I say order matters, I mean the thing at index 1 comes after the thing at index 0, but before the thing at index 2, right? There's an order there. And if you've got something like sets, part of their functionality is they manage duplicates in their way. But if we consider the list, you know, we can index the list. The list has a beginning and an end. If I gave you a list and I said, where's the beginning? Where do you point? Index 0, right? And then I say, what comes next? You're like, well, the index 1, right? It's a silly question. It's obvious. And then where's the end? Well, the other end. The elements exist in some order. Like I was saying, index I comes before index I plus 1, but after index I minus 1. And they're easier to do linear searches on. I mean, they kind of go hand in hand. So lists are great. They're very general. And you've been taking advantage of these features of the list, but you've never really, like, you've been taking advantage of the features, these properties of the list that you've been interacting with at the level of this is what a list can do. But again, under the hood, there's a lot of code. There's a lot of algorithm that's in there, and it needs to be programmed. Data structures are, along with things like, you know, for the first like 2/3 of the semester, every new tool we added to the toolbox that you as programmers have in your toolbox, it started with things like variables, functions, ifs, loops, right? These were tools you were adding to your toolbox. And something like an if statement is just something that's intrinsically built into these programming languages. If you type if, it even comes up with special, like fancy syntax, right? Because if is just a part of the programming language. But, I mean, lists are too. We get the lists with Python standard library, but they're like, if you were to take like, here's the Python programming language, and lists are coded in Python, right? So within the list, somewhere within Python, if here's all the code that includes like your ifs and loops and everything, with the ifs and loops and everything, people built a list, right? So awesome. And they give it to us to use. But unlike the tools that we got in the toolbox before, a data structure like a list, again, it's another tool to add to our toolbox, but it's far more complex. It's actually built of all these smaller tools that were put together to make a list. And we interact with the list directly, not the underlying lower tools. So as we're adding more tools to the toolbox at this stage, they're becoming more abstract, intricate, complex things that we can use. Like a dictionary, we're not going to learn about dictionaries right now, other than like how to interface with them. But a dictionary is a rather complex data structure. If you open up that hood, there's a lot of crazy stuff going on. But you know, we've already added the dictionary to our toolbox. And there's only more and more complexity that comes, and we just add them to the toolbox. But like, you can almost think of it as like the size of these tools are getting bigger. Not physically bigger, of course, but I mean in terms of how much lower level stuff is contained within the tool, if that makes any sense. The lower level stuff being like your ifs, your loops, your variables, and how all of those come together in a certain way to make a list. So there's a lot of stuff under there. At this point, I've been careful to be like, okay, don't think about what's going on under the hood. We want to interface with the list at that level of abstraction. We don't want to think, like, when I append to a list, how's it actually doing it? I've been saying, don't worry about it. It just, when you append to a list, it adds to the end of the list. Isn't that great? Awesome. But it's getting to the point where we know enough, and maybe you're curious enough to be like, well, but how does it do that? Like, what's actually happening there? And in order to be a good programmer, obviously you want to have these tools in your toolbox, but you want to know how those tools actually work. So up until now, I've been like, don't worry about how they work. They just work. Now it's starting to get to the point where we want to say, okay, how does it work? I want to know how it works. So what we're going to do is we're going to make a very basic data structure. To be clear, because of the nature of Python and some other things and how much time we really have at this point in the semester, this example is going to be a little bit contrived, all right? So be aware of that. That's not to say it doesn't give you the general underlying idea of what's going on here, but it is. So if you're thinking, this feels kind of like he's forcing it, maybe a little bit. You're not crazy. So what we're going to do is I want to say, okay, a list is a very generalized data structure, but I don't want a very generalized data structure. I want to write a program to keep track of all the students in 161. okay? That's what I want to do. So here's what I'm going to do. I'm going to make student objects that are going to be a representation of each student. And the student's only going to have a couple of attributes. It's first name, last name, and student number. It's not really going to have any functionality associated with it other than maybe a repr and an equals, because I don't really need any functionality. The purpose of the student class is to just store data. And then what I'm going to do is, like if I've got 100 students in the class, well, how am I going to manage that? Well, I could put them in a list, and there's nothing wrong with that, but we're going to make a specialized version of a list specifically for managing students based on how I want to manage my students. So we're going to make a course class that's going to manage the student objects. So the student objects are the objects we care about, but the problem is we're going to have a lot of them, so we need a way to manage them. So this is where the course class comes in. The student class is just going to keep track of some important information and an EQ and a repr, because they're handy for testing. So I'm just going to copy this, paste it, get rid of this. And we'll take a moment to talk about what we're seeing here. So here we go. We've got our initializer, our constructor. All we have is first name, last name, student number. Great. We've got our equality. But what do you notice about equality here versus what we've done before? Well, we did do that before. That's just checking, is the other thing even a student? If it's not, then they're not the same. If it is, go ahead and do the check. Take a look at the construct. What are you going to say? Yeah, that's exactly what's a little funny. Every time before we wrote equality, all we did was just compare all the attributes. But whenever we were checking equality before, when we were checking all the attributes, that's not because that's what equality is. That's because we decided that's what equality was between those instances. So here, at the end of the day, I could have made it check all the 3 attributes. If they're all the same, they're the same. But here I'm saying, you know what? In order for students to be considered equal, all that matters is that their student numbers are the same. And is that a reasonable decision to make? Why? And then they could just change. Yeah, absolutely. So the names can change, but their student numbers can't. And student numbers, assuming they're at the same university, they got to be unique. So really, all that matters is their student numbers. So that was the motivation for this design decision. But be aware, this is a design decision. This is a decision I made as the programmer based on what this program was for. This wasn't a decision about something that's fundamentally true in Python or is required. No, it was a decision I made. And now look at the repr. The repr is a little different than all the other reprs we wrote so far too. Before, usually what we did was the convention was class name, parenthesis, attribute, 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 close parenthesis. That's what you did. But that convention is the convention you follow if you don't really have something specific in mind. But based on how I want this program to work, I wanted my repr for a student to be formatted a little differently. Something a little bit more helpful for the purpose of this program, to just tell me information about the students in my class. So what I have here is the last name, comma, first name. Who remembers what /t is? Tab, very good. Tab, student number. And if you're saying why? Because I said so. This was a design decision. It's not because it needs to be this way. It's because I wanted it to be this way. That other convention, you only use that convention of, again, class name, parenthesis, attribute, 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 close parenthesis. You use that convention when you don't really have anything else in mind, because it's a hell of a lot better than object at OX7BAFEE212, right? But here, because of what I'm going to want the program to do, and we'll see shortly, this is how I wanted it to be printed out. And let's do a quick little test of this. No unit tests or anything. I'm just going to make a student object, a student equals Bob Smith, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. There. And yeah, that's what I wanted for repr. Let's make another student. Oop, that's not what I wanted at all. When I hit run, look at this code. I'll give you 20 seconds. Look at this code. When I hit run, what do you expect to see printed out? Don't yell out the answer. Just come up with an answer, and then in a moment we'll yell it out. All right, on the count of 3, yell it out. 1, 2, 3. Why true? Because the student numbers are the same, and that's important because, well, that's what EQ is defined as. So even though their first name, in fact, here, we can do this. And it's still going to be true. The second one doesn't even need to have a first and last name. Their student numbers are the same. That's all that matters. Now, how about this? Whoop, nope, not that. False. They're both Bob Smith, but their student numbers are different. So obviously they're not the same. Cool. Okay. Any questions so far? This is a very simple class. That doesn't mean it's trivial. So if you have questions, ask. But it's a very simple class. There's no functionality really associated with it. It's just data. That's all it is. So effectively, the purpose of this class is to just group relevant information together in one place, and that is an instance of a student. A student has multiple values associated with them, but we can kind of store it all in a single student object, which is great. I'm going to hit pause on this and take a step back. You remember when we started learning about objects, classes, and whatnot, I was saying, you know, objects are a great way to combine data and functionality. I want to be clear about what I'm saying. I don't mean it's a great way to combine data and functionality together. What I mean is it's a great way to combine data together and functionality together. And if you really want, data and functionality together, where you kind of have that data also have some relevant functionality associated with it. But there's a lot of programmers out there, when it comes to design of their programs, they actually really don't like to combine data and functionality. They really like to keep these things separate. So if you're thinking to yourself, well, but the way I could design my program, I need to have it combined. Well, you could probably redesign it such that it doesn't need to be that way. And there's some design decision reasons. That's kind of hard to motivate at this stage, but it's a lot easier to reason about your code, to test your code, when you have data and functionality kind of separated. Now, to be fair, EQ and repr is functionality, right? It is there, but this is functionality that's going to be more about, really the functionality is strictly just like about that data. So it's not doing anything weird. That doesn't mean you can't combine data and functionality. together. There's nothing wrong with that, but there are design reasons why you might not always want to do that. So just be aware of that. This is not a core concept I want you to be overly concerned with right now. This is something that if you're in raise your hand if you're taking 162? So if you're in 162, this is going to be something that's going to be emphasized more as we go. But just as a heads up right now, when I say combine data and combine functionality, I didn't necessarily mean together. I just meant a way to combine these things kind of in some unit of thing, an object. All right, cool. Okay, questions about the student class before I move on to the course class? Yes?
I just have more of a general question.
Yes?
So objects are like what we're looking at, but what is it? So the student is going to be an instance of the student class.
Yes.
But then it's also a class, and then the data structure is also a class?
So, classes are, this is a class. This, a student, is a reference to an instance of that class. And we usually call instances of the classes objects. All right? A lot of programmers are going to interchange these words. So, and then if you're like, oh no, how am I going to keep track of it? At the end of it's kind of like arguments and parameters. There is a difference, and I like to make it clear. You know, these are the parameters. The parameters are to variables as these are the arguments, as arguments are to values. Okay? But in the same way, people interchange those words all the time. Programmers will do it, and programmers will know what people mean based on the context. It's going to be the same thing with like classes, objects, instances. People are going to mix them up. I try my best to be as clear as possible. I've probably mixed them up in the past and will continue to mix them up. But there is a difference, and I'm glad you're asking. Now, when it comes to data structures are a specialized type, a specialized idea of a class that we're about to make one. The course object, the course class we're about to write, is going to be a data structure. But there's not really something you would look at it to immediately be like, oh, it's a data structure. You'd have to look at the code and be like, oh, I see what they're doing. Okay, they're making a data structure. So don't get too worried, but great question. Other questions about this class before we keep going? Okay. So the next thing we're going to write is a course class. At the end of the day, the course class is really just going to be a list. Okay? In fact, we're going to hijack the list. But we're going to build on top of that the functionality that we only really care about and how we define like the repr and add and remove things. Like we're going to write code to control how that list is being used. And before I continue, we are writing the course class. I know we are writing the class. Someone wrote the list class in Python. So there was someone or a collection of people that wrote the list class. So there are people that use the list class, like you, and people that wrote the list class, like the people that wrote the list class. Now, the people that wrote the list class probably also use the list object themselves, right? But you got to remember, there's kind of like this line of people that are using it and interfacing with the list class, which is like 99.9999999% of people. And then there's also the people who are writing the list class, which is the remainder. So you're the person writing, we're writing both right now. We are writing how it works, we are building it, and then we're also going to use it. So because of that, there's going to be some ideas that are perhaps not immediately clear. Because you got to remember, I'm going to make some design decisions, we're going to make some design decisions for the code in our course class that we are aware of. We're aware of this code. And you're going to say, like, well, why would you do it that way when you could just do it directly? And I'll point out some examples as we go. And you're not wrong if you're thinking that, but the point is, the person using the course class isn't supposed to know what's going on inside the course class. You do by virtue of writing it, but in general, the person using it doesn't give a shit about how it works. They just want to use the course class. So there's a lot of mechanics underneath there that doesn't matter to them. You got to remember that. So when you're writing it and you're like, well, they could just do it this way, right? It's only one extra step, whatever, who cares? You're right, but they don't want to give a shit about that. They don't want to care. So we're hiding some stuff from the programmer using this class because they don't need to know it, it doesn't matter to them, and it just simplifies everyone's life. So let's continue. So the course is just going to be a collection of student objects. Ultimately, the student objects will be stored in a list, so it's just going to be a list. But we want to make use of a class for the specific functionality we are going to care about. Oh, okay, I'll finish this point here, and then I got to hit something. We will have the course class control access to the list of students through a variety of methods. So we're going to want a method to add students to a list, to add it to a course, which is just adding it to a list. We're going to write one to remove students, to get the size of the course, just how many students are in the list, and a method to check if a student exists in the course, and a repr, because it's always good to have a repr. The repr really is the functionality I care about if I'm writing this program. I just want to have details on the students in my course. Now, pause on this for a moment. Not 4 minutes ago, I just made a big stink about data, functionality, right? And then there's always like design decisions around it, and a lot of programmers are going to have a lot of strong feelings about combining data and functionality. But there is an exception, data structures. By virtue of what a data structure is, you are going to be combining a lot of data and functionality together. Think of a list, right? A list is a lot of data, but a list also has a lot of functionality associated with it. Data structures are typically very stateful things in your programs. There's a lot of data, there's a lot of functionality, and things are changing, and that's just the nature of data structures. So if you're about to be like, well, hold on, you just said don't combine data and functionality, and that's all you're doing right now. It's, well, this is because it's a data structure, and that's kind of the thing. All right, let's start with the course class now. Now, look at this constructor and tell me if you notice anything interesting. There's two big things here I'd say that I think that stand out to me. But look at this code and what do you see? Anything that stands out? Yeah, so self.students. So let me break down a little bit of what you're pointing out here. How many parameters does this constructor have? Yeah, I see you're going like 1, but 2 because it's self. You're right. Self is a funny one. I would typically just say 1. We ignore self. So there's 1, the course name. And there's a course name attribute. But how many attributes does this class have? 2. Up until now, it just so happened that the number of parameters our constructor had and the number of attributes our class had were the same. That was just dumb luck. The parameters and the attributes aren't overly connected. The attributes your class have is the attributes your class needs. The parameters the constructor has is the parameters the constructor needs. Here, when I create a course, all I want to do is give it a course name. But when I create a new course, remember, a course is going to be a collection of students. When I create a brand new course, there's going to be no students in it. I need to add the students to the course. So, I mean, we're going to need a variable, an attribute, to keep track of the list of students in our course. So at the beginning, when we create a course, a new course, a brand new course, there should be no students in the list, in the course. And there's nothing I would need to provide to this constructor as an argument for creating an empty list. There's nothing I need to do. When I create a course, I need to remember its name, I need to know its name, and I need to create an empty list. There's no parameter that matters for creating an empty list. So even though there's no parameter here for this attribute, that doesn't matter at all. It never mattered. Why do I have it? Well, because when I create a course, I'm going to need a list that starts as empty that I'm going to put the students in. So I create it in the constructor, because that's what a constructor's for, the setup code for the class. Any questions about that? Yeah?
Is the underscore relevant before the student?
Yes. And that was the other thing I wanted to talk about. It also starts with an underscore. Now, the fact that it starts with an underscore has no functional meaning. It is a convention. It is a convention that means this. Pause. We're going to pause for a moment. Right here, we're looking at the student class. And the student class has three attributes: first name, last name, student number. And we can access the values of these attributes inside the class, like right here, right? Or right here, I can say, well, self.last name. So I am accessing these attributes of that student class within the student class. But I'm also allowed to do this. I can access those attributes from outside the student class. Right? Cool. And I can, okay, it's Bob, right? If I were to make a new course, I can access that attribute from outside the class. I can access it from within the class, although you don't really see it because we haven't written anything really yet. There's only a constructor here. I can always access these attributes from inside the class, and I can always access them from outside the class. That's just how it works in Python. But sometimes a class will have attributes, and when I say sometimes, I mean a hell of a lot of the time. A class will have an attribute that you can access from within the class. Obviously, I want to be able to access that attribute from code inside the class. But I don't want anyone touching this code. I don't want anyone to touch this attribute outside the class. Leave it alone. And so the underscore is a convention that means, okay, so this is an attribute called students. But because it starts with an underscore, it means don't touch it. You can touch it from within the class, but outside the class, don't touch this class. Like the attribute, don't touch it. Leave it alone. You're not supposed to. In fact, this convention is so strong that, look, if I go here, watch. If I say a student dot, it'll tell me, look, you got your first name, last name, student number, right? It does this code completion here for me. This is just Colab being helpful. But if I change this to a course dot, it's only showing me course name. The reality is, I can, because it's just a convention, I can do that, and Colab will be like, yeah, fine, it's there, yeah. And I can do it, and it gives me that empty list, but the underscore means I'm not supposed to be using the code like this. So the underscore is a signal to mean just don't touch it outside the class. This is important for the inner workings of the class, but outside the class, you're not supposed to interact with this. You can add 2 underscores as well. And sometimes people think that means you can't access it, but you really can. It's just there's more steps involved, but it's a single underscore is the convention. For anything within a class that you don't want to be accessed outside the class, but if it's important for the inner workings of the class, but not outside. In other programming languages, like Java, there's actually, it's not a convention, there is a keyword you use to enforce this convention. So it's not just like, well, you do this convention, but you can break the rule. No, the programming language provides a way where if you try to break the rule, the program won't run. It'll break. In the same way that, like, there's a constant. In Python, all uppercase for your variable name is convention for a constant, meaning you don't change the value of that variable within the code. Although Python will let you. And it won't get mad at you if you do. Other programmers will, but the code won't. In a lot of other programming languages, you can say const or final, and it actually makes it final. So if the code tries to change that value, you're not just breaking a convention, you're breaking your code. The code won't even run. You'd say run, and Java or C++ will go, no, you said this was constant, and you're changing it. Or you said this was private, that's the keyword you use to mean leave it alone, like the underscore. You said this was private, but you're trying to access it outside. I'm not going to run. I'll take a moment to say a lot of new programmers think like, oh, well, okay, the other languages allow you to be more restrictive, but I don't want to be restrictive. I just, like, whatever. I'll just do what I want and just make it work, and I'll just be aware of everything. And I know you might think that, but you're wrong. You really want to be able to very meticulously control all this stuff because it makes your code, you might feel like it makes your code easier to program when you're starting. Whatever you're doing. I don't mean starting as a new programmer. I mean starting any particular project. But that's only true for like this much of the work. Once you get past that much of the work, you realize, oh, you're screwed. You've messed up. Anyways, so underscore students, it's an attribute. It's important for the inner workings of the class. We're going to be accessing it with inside the class. But outside the class, we're not supposed to directly touch it. We're supposed to leave it alone. Any questions about that? Good observation. Who else noticed the underscore but thought nothing of it? Okay. Pardon? No, 1. Only 1 underscore. This is like the 2. This was only the 1. You can add 2, and it means something a little bit different. Don't add 2. All right, yeah. This is just explaining that. Now let's add a size and add. You'll notice these are hilariously simple because all we're doing is just hijacking the lists functionality. Let's start with add. If I want to add a student, just append it to the list. Self._students.append, you add that student. Great. So we're just hijacking the list's append to add something. For size, if I want to know the size of this, like how many students in the class, just hijack the length of the list. That's all it is. Easy peasy stuff. This is great. So let's do a quick check. If I say a.add a student, Well, here. I can access it. I'm not supposed to. I'm being an asshole right now. But I can access it. And you can see, well, now that attribute is that list with just Bob Smith in it. But notice how that Bob Smith, rendered. When the list prints out a list, someone wrote the code to say, okay, start with an open bracket, and then give me the string representation of the first thing in the list, then the next thing in the list, then the next thing in the list. The list's repper just asked that student, what's your string representation? And where was the string representation of the student defined? Right here. So that's kind of neat, but more on this shortly. Size 1, because there's only one student in there. Cool. But all this did was hijack existing methods in the list class. Cool. Now, I want to write code to remove a student from the class. And I also want to write code to check if a given student exists in the class, right? So I want a method to be like exists or contains. And I want to give it a student, and I want this class to tell me true or false, whether or not it's in that list or not. I also want to be able to write remove, go remove such and such a student. And then it goes and removes that student. But think about, look, if I want to know if a student exists in that list, I got to do linear search, right? And if I want to remove a student from a list, I got to find that student first in order to remove it. And how do you think I'm going to find that student? A linear search. So I've got two methods that need to do a linear search. And there's nothing wrong with writing the code to do that functionality within their respective methods. Write the linear search part in your contains and write the linear search part in your remove. But of course, we're good programmers that have been aware of functions for a long time, so let's just write like a function to do the linear search that we can call in both. But this is a class, so we don't really have functions. We have methods. But this method, this linear search method, isn't important for the course class other than the fact that it's used to help other methods within the course class that I do care about. Contains and remove. So what I'll do is I'll write a method, and I'm going to call it find. And this code right now, if you can't look at this code and immediately know what it's doing, you should feel terrible about yourself. Of course, I'm being silly. But what is that code doing? It's just a linear search. But this is giving me the index of the thing I'm looking for. So enumerate over self.students. If s is equal to the student I'm looking for, which is the parameterized value, the student, if s is equal to the student I'm looking for, return the index. And if I ever get to the end and I don't find what I'm looking for, I return -1. And I could probably, I'd say, I can improve this with the constant, right? Any programmer would see the -1 in this context and know it's a sentinel value. It's that special value that it's clearly not an index of where something exists. It means it wasn't found. But there's nothing wrong with making your code more readable by adding a constant in there. Not found. How does Python know how to compare students? I'm checking, does some student, the first student in the list, does it equal the student I'm looking for? The next one, does it equal what I'm looking for? How does it know? Well, I defined equality on students right here. So that equality, it's only working because I defined what it meant for equals on student. And what else do you notice about this method? What sticks out like a sore thumb? The underscore. What do you think that means?
We can't use this method as 5.
Yeah, it's the exact same meaning as it is with the attribute, but now we've applied it to a method. It's a method that exists within the class. It's important for the inner workings of the class, but it's not meant to be touched outside the class. It is what we say private. That's usually what we would say in this context. So we're going to use this method inside the class, but we're not going to access it outside the class. Just like the attribute, I can access it outside the class, I'm just not supposed to. And again, a course dot, Colab is being helpful enough to not show that private method in the like pop-up list here for code completion. And by the way, I'm pretty sure this is a relatively new enhancement to Colab. I'm pretty sure last year at this time it would actually show those, but they got rid of it, which is a good thing, I think. Anyways, so there's the find, and now to write our contains method, well, this is hilariously easy. Call find. Here, let's change this to not found. Contains, all contains does is calls find and checks that if find returns anything that's not a -1, return true. If find return any index, any integer that's not a -1 or any other any of its valid returnable values, that's not a -1, that means that's the index of where it was found, meaning it was found, return true. But if it does return not found, this will be, does not found not equal not found? Well, that's false, it returns false. And then remove. Now, the first thing I do with remove is I check, does the object I want to remove, does the student actually exist within the class, within the object? If it does, then I just say students.pop self.find the student. We'll come back to this. If this is false, though, meaning if the student's not in that list, what should I do? Should I ignore? Should I crash the program? Does that mean something really bad happened? What should I do? Well, I don't know. I wrote this class. I don't know what you want to do if you're using the course class if you try to remove something that doesn't exist. So what I'm going to do is I'm going to raise an exception. All right? So here's a perfect example of where an exception would pop up. You try to remove something that doesn't exist there. What do you want to do? That's a weird thing. What do you want to do about that situation? If it does exist, well, if you call pop on a list, that means, and you give it an index, it removes the value at that index. So if I had the list like A, B, C, D, and I said pop 1, the new list would be A, C, D. It just removed that middle thing. It eliminates it and moves everything up. So we're going to pop the thing at the index where that student I want to remove is. Cool. All right, we'll end here. Any questions before, though? No? All right, I'll see you all later.